So initially, the state of our wave function is a superposition of going through the top slit and the bottom slit. And the exact details of that interference pattern depend on whether this superposition is a plus or a minus or some other phase. And we've also got this two-level system here. And initially, it's got nothing to do with our other wave function, so our initial state is separable. So we just take the tensor product. And this state we're going to have, say, in the z direction, the spin will be down. So that's our initial state. Now the real question, of course, is does interaction with this two-level system count as a measurement or not? If it counts as a measurement, they're going to jump to either psi1 or psi2, because we're going to know which slit it went through. And if it doesn't, it's going to do something different. Now we know how to expand this out, because we know that the tensor product is linear. So in other words, our total combined system is in the initial superposition of the particle being up at the top slit and the spin being down, plus the particle being the bottom slit and the spin being down. And these two states here are parts of the combined Hilbert space. Now the evolution of this, we know what this is going to do. We've designed our interactions such that if we have a particle down here at the bottom slit, then it's going to change the spin of this. So whatever unitary operation we do to this big state, we know what it's going to do to this. And we also know what it's going to do to this. It's going to not change this at all. So if the particle's up at the upper state, it's not going to change the spin of our two-level system. And therefore, we know what the unitary applied to this whole thing is because unitary operators are linear. So remember, our original question was, what do we see on the screen? Do we see an interference pattern, as though there'd been no measurement at these slits? Or do we see two blobs, as though there had been measurement at these slits? And it's a little bit hard to see from here because we don't have the mathematical tools to know what happens. We know what happens if we measure the whole thing. We get wave function collapse according to the normal postulate. But what happens if we only measure in one subspace over at the screen? Okay, let's look at this. Supposing we were to measure the z direction of spin of our two-level system. So if we measure the z direction of spin of that, then we'll either get plus a half or minus a half. And if we get minus a half, then the wave function will collapse to this, in which case we'll find that if it definitely goes through here and we don't get any change of our spin, we'll get one big blob. All right, so we'll see that if we measure spin z to be down, that will be correlated with one big blob. And we see if we measure spin z to be up, we'll get that correlated with another big blob. Let's look at what happens if we measure a different basis of this. Now all I've done here is I've expanded the eigenstates of the sigma z operator into the eigenstates of the sigma x operator. And so it's just a linear combination. It's a two-level system, and so this eigenstate here has to be some linear combination of mx equals plus and minus a half, and it turns out it's just the difference. Mz equals plus a half is just the sum of the two. And so all I've done is expand that out, and then of course, because I know how tensor products work, I can expand all of this out and collect all the terms with the mx equals plus half together and all the terms with the mx equals minus a half together. There we go. And so we can see that by collecting it that way, we see that if in fact we'd measured the x direction of the spin of our two-level system, so if we measured the x direction of this two-level system, we would have got either plus a half or minus a half. And in that case, this wave function would have collapsed to give us this state for our wave, or that state for our wave, depending on whether it was plus or minus a half. So is this process of entanglement, where we take our initial state of our wave and entangle it with this spin half system, is that measurement or not? Our first thought might have been yes, because if we measure the spin of the spin half particle in the z direction, we get either a blob on the top or a blob on the bottom. However, that information, whether it's plus or minus this superposition, hasn't actually gone away, because if we instead decide later on to measure the spin of that particle in the x direction, we will see that there are in fact interference fringes. So how does that work? When we do this interaction, what we see on the screen is in fact big fuzzy blobs. But those big fuzzy blobs are now correlated with information back here on this two-level system. And if we measure the z direction or the x direction on that two-level system, we will get different correlations. So if we measure the z direction, we'll find out whether it was a blob from the top or the bottom. And if we measure the spin in the x direction, we'll find out whether it's one interference pattern or the complementary interference pattern that kind of fills in all the gaps. So all the constructive interference here is destructive interference for this state and vice versa. This idea of making a quantum measurement, if you will, or getting very close to it, and then undoing it afterwards, is known as quantum erasure. because entangling these two systems is like making a measurement, but later on we can erase that measurement by manipulating our system again. Now, in order to deal with these systems properly, in order to be able to really talk about what you measure when you only measure one subsystem of a combined system, we have to talk about open quantum systems, and we have to introduce the idea of classical uncertainty in quantum systems, which means we need to go to a new method of describing quantum systems called the density matrix.